Wired up.
Are you wired up?
Yeah.
Are you pumped up?
I'm pumped up. Ready to go.
Okay, tell us a little bit of you, a lot of you.
Okay. Thank you for inviting me here. It's been wonderful so far. So what I'm going to talk about is actually a little more deeper technical material, which is based on a sort of journey that I've had since year 2010 when I was department chair at ECS department, and one material scientist professor, famous, and we were working on data mining. That time it was called data mining. Now it's all AI. And he said, we have these problems in material science, and I'm wondering whether it makes sense. We have all sorts of data, and wonder we can collaborate and see if we can create something different and new and discoveries. And that was the beginning of my journey in material science. Before that, when I thought of the material, I thought of clothes that I was wearing, and nothing more. So that's how I got into to material science. Over the years, we've collaborated with maybe 10, 15 different universities, NIST, and some of my team members here, supported by many agencies over there. Not currently. So this is a 10-year plus year journey, and then we have a lot of course, publication, but all the code, all the AI code, inference models and others, everything is available on the web. And there are tools that are available which are used by hundreds of people around the world. So before I get into my talk, this was a recent release of an edited book by me and Jeffrey Fox and Tony Hay.
Can I just interrupt to say, Jeffrey Fox, Multicore World 2018-2021, Tony Hay, Multicore World 2014-2015.
Oh,
sorry.
All right. It's like a 6-month-old. They contributed chapters from across the globe, including SKA folks. Satoshi has a chapter in it. So this is just some new recent development last 6 months. All right, so just to give you a quick background about the work that I've been doing over my career, it's essentially been in HPC domain and data mining. I started, my focus within HPC had always been in data-driven computing, high performance data access, and so on. And then we've been collaborating with medical folks, life sciences folks for many years. I got into social media data mining, and that's how I started a company which was fortunately had a good exit, was acquired by another company. So the focus today is material science. And so let's get started in this. So one of the things I learned, which shouldn't have been surprising, was that the landing gear, for example, you see in a plane, and the material that goes in, it can take 20 years from conceptualizing to being in a real product. So certain materials can take a long time to be discovered and then come into product. So one of the goals of Materials Genome Initiative and others was, how can you reduce the time to market by a factor of 2 and reduce the cost by a factor of 2. That can make a huge difference. How can you accelerate discovery? And what we have to think about is everything is a material, right? I mean, what we wear, what goes in computers, to missiles, to drugs, and so on. So in this talk, what I'm going to go through is, okay, so we have these old ways of doing, I shouldn't say old ways, we have traditional ways of doing science and discovery, which include simulations, experiments, and you have all this data available over a period of time, which has knowledge buried in it. And how can I now bring in data mining, AI into this process to discover information and then apply that to do new discoveries, right? And that is the focus of this sort of step-by-step journey. And there are a lot of limitations in what can be done using simulations and experiments and so on, how AI can help, and some examples of that. So over that, since 2010, we have, with our collaborators, have had a lot of publications, okay? So the green ones are the ones in like Nature or Computational Materials, or a lot of material science types of journals and conferences, scientific report and so on. And the red ones are in computer science type of one. So the point is that work has been considered important and recognized in both application domains and so on. It's not just some CS work and then, you know, people in application areas, materials areas say, oh, what is all this? It's not useful and so on. So what I'm going to describe is a bunch of these publications are on this work that I'm going to describe. And very quickly on, and I'll show this later, it's all available on the, whoops, it doesn't, I can't go to the website here right now. Anyway, I'll go later, figure it out how to do it. Okay. So what is the process in designing materials? Okay, this is also something that I learned. What we are really looking for is performance of a material. Performance can be anything, right? I mean, semiconductors, you require certain types of performance, or if it's going into landing gear, what is the strain it can handle, and so on and so forth. But what happens is you start with the processing of something, right? Some raw material or combination of raw material. And there are a bunch of things that a flow in materials design, bunch of steps that it goes through. So the processing is what influences the structure, right, of a material. And structure influences its properties. And the properties in turn determine what performance you're going to get. So there are two types of problems. One is knowing a material, how do you predict its properties, right? But what is called the inverse design problem is, hey, I want certain performance for this type of, because I have a design goal in mind, what type of materials, what would be the processing and so on, what would be its properties, structure, and then how do I get to that structure, what type of processing. Now, important thing to remember is that you can get to the same structure by different types of processing, right? You can get to same properties by different structures. So you have to also determine which is practical, which is cost effective, and so on and so forth, right? So this is a very, very challenging problem. And typically people will work in pairs, processing to structure, structure to properties, and so on. Okay, so the complexities are enormous, right? So we have this periodic table, we have different types of properties of materials, electronic structure, conductivity, whatever, etc. So there are, if you take the, you can have any combination, right? If you give it to ChatGPT, it does, you can give 10 of these, and I don't know what the output would be, but materials can have lots of these elements connected in certain way, and we don't know what the properties would be or could be. So there are trillions of possibilities. So now stepping into the reality of what exists in the material world, and one of the ways, which again I learned, is simulations, right? And so-called DFT simulation, right, which is pretty common. And over the several decades, with the help of high-performance computing, simulations, massive amounts of data has been collected, right? And there are different databases. So, for example, OQMD, the first one, there are around 1 million 1 million simulations output that is available in this. There is a materials project, another set of data sets, and so on. And DFT simulations are very, very expensive, right? So simple problem definition that we started out with was, can we learn, and now you can probably call it a meta or some surrogate model type of thing, but can we learn from these simulations? Remember, simulation is an approximation of real material, but it's not the real material itself. So it's an approximation. So can we learn from this data set, apply learning and machine learning, AI algorithms, and create certain predictive models? So things that have taken huge number of years, or simulations that can take a lot of resources and time, can we then train the model and create an inference engine that can predict in milliseconds? And if you can do that, then you can scan all sorts of combinations of materials in days, right, for properties, right? So that there you can potentially look at try to address inverse design type of problem, right? So that is the goal. So now when you go down this path, you have to, this is real evaluation. You have to figure out what works, how well you are doing, can you validate, et cetera, right? So in this busy slide, there are only 2-3 points that I want to make. So one is there are hundreds of thousands of DFT simulation data that is going into the learning. When you do traditional data mining, right, so apply machine learning, you have to learn features, which is a very difficult thing to do. It's not so easy to manually design features. So the table on the top is derived features of combinations of some of these materials, right? And when you do DFT, and again, I'm not an expert in that user, you have to also know the structure information, et cetera, et cetera. So one fundamental question we wanted to ask ourselves was, can I create a predictive model, AI-based model, where all I need to provide is an elemental fractions? None of those features, none of those structures, and so on, how well can I do, right? So this is what that shows. So you're doing architecture search and so on in machine learning. So what these charts basically show is that if you used features like before and you applied traditional machine learning like random forest and so on, is there a pointer somewhere? Okay. So the orange line here essentially shows the error, mean absolute error in predicting. This is one of the formation energy properties, one example of this, that as you increase the data size, as more data is available, now using only elemental fractions, so you don't need to provide structure or other types of features, and you are able to do better than traditional machine learning. Oh, other way. Okay. And this line here and the orange line, so you are pretty close to what you saw from DFT. But the good thing now is, now you can give it huge number of unknown combinations that have never been simulated, are not known, and then you can scan through millions of combinations of ternary materials. So how do I go to the website? Let me just try this. Oh, okay, let me just show you this. So if you go on this website, you can, this is an inference engine running in real time, and there are other inference engines within materials. You can go put in any material, say what properties you want to see, and you say submit, and it's going to give you, I mean, interpretation is always done by material scientists and so on. So, and it's going to very quickly give you. So now, if you could have done DFT of this, and you would get similar results like this, which can take huge number of resources and time. So you can now scan through this. Okay, so now the question is, if I go, so this is the first step, right? We give elemental fractions, we can predict properties. Okay, this is, this slide should not be here, but it is here. Okay, so I'll talk about this anyway. Anyway, so then you can, so you start with an architecture, you do some experiment. Now you can go deeper into different types of architectures. You do residual networks and so on. As you increase the data size, you can get better and better results. So this is an architecture search type of exercise, where by using different architectures, now you are able to take advantage of larger data sets and further reduce the errors. So if you look at this chart, the point of this is, as the data size, more data is available to you, and you search the right architecture, then you are able to continue to reduce the error that from these predictions. AI-driven predictions for these. Okay, so again, these are pretty recent publications in this space. Okay, so the next question is, what is the error that you are getting with respect to DFT results, right? That's important. And these are considered very good from material scientists' perspective. So we learned from DFT data, created a model which is predicting really well. You validated the error. Error is within acceptable bounds from the DFT simulation data. But if you take a step back, you realize DFT simulation itself is not an experimental result. It is also a mathematical approximation of a material, right? So it has error compared to the real material. So is that the right way to even evaluate, right? Because you are evaluating with, as compared to simulation result rather than the real material. So that gave us, we said, okay, so what we should do is we should evaluate the result of the prediction which learned, or models learned on simulation data, but against the experimental properties, measured properties. So now if you look at the error, which is much higher compared to the experiment. So you learn from simulation data, you take experiment, only subset of experimental data is available, right? These you have, let's say, 1 million here, only few thousand results. That I'll come to later. So now you're trying to measure against the error against the real experimental data. But now, and I didn't talk about this modeling, but now you can build your deep learning model based on experimental data itself, which is much smaller, and you get this error, which is also pretty high, but it's slightly better than this. So we haven't, I mean, we made progress, but we haven't solved this problem, because goal is to come up with results that are closer to experimental data, right? So that's what I talked about. But experimental data, each company has its, each lab company, they have in their silos, their groups and so on. Experimental data is not as widely available. There are specific, there are challenges in getting that, so it's much smaller, right? So the question then we wanted to, so this is the next step in this journey. We said, okay, we can learn from DFT, and now today, for example, this is called, popular word is probably fine tuning, but it's, technical word, transfer learning. So the idea was learn from DFT data and then take smaller, much smaller, 2 orders of magnitude smaller experimental data that is available and do the transfer learning? And can we take a step closer to our goals? So what this shows, right, so this is another work there. Can AI replace DFT, at least reduce the requirements by order of magnitude? So what this shows is that this is with DFT data. So this is the baseline with DFT. So this is when you use the experimental data, which is the ground truth, but much smaller, so you can't learn much. Learning is not easy from small amounts of data, which is another challenge that we've been addressing. So this is learning from experimental data, but the error is pretty high because you have small, right? But now you learn from simulation data and then you do transfer learning with experimental data, you're able to do better. So if you look at this, right, one of the goals was, can we do better than DFT itself, right? So what that essentially means is, can we reduce this error by this method, which is lower than what DFT's error is compared to the experiment? And this is actually lower, not too much lower, but question is, can you sort of replace, at least accelerate this process of simulation and experiment by AI? So then the next challenge that we learned is that when you do experiments or when you do simulations, you are only doing it for 1 or 2 or 3 properties, but there are so many different properties of all these materials, right? So one of the dimension is the material composition, structure, property that you can learn. So the question is, can we build AI models that learn for one property for which a lot of data is available, and then can you create architectures and learn, do transfer learning type of mechanism to predict other properties that has not been seen before, right? So basically that's the approach. You learn for one property and then you do transfer learning type of approaches for other properties. And this is a very quick summary of that, which shows, okay, you have large data sets, you learn for properties for which the information is available, you do transfer learning for other properties, and so on. There are other challenges here, which I won't go through, but most important thing to remember is that in 38 of the 39 case properties, right, this model did better than if you just took the data that is available for that property, simulation or experimental data, right? So the learning available in the simulations for other properties and so on helps you actually do better than in other properties, right? And one of the other things that we were able to discover was, so this is the in distribution. This line is the data, you look at the data distribution, so you are able to do interpolation, so this is pretty good here. But it was also able to do better for distribution it hadn't seen before, right? So it's the extrapolation part of it. So in summary, this I tried to summarize a lot of work over the years of step by step. How do you incorporate AI, and then try to understand, solve a problem, and make step by step see how close can you get to the accuracy that is desired, the time that you need, etc., etc. So I shared that journey with you. One of the once people from materials group of Toyota in Japan, they came to us after seeing some of our work, said, okay, we want to work with you. We are working on designing batteries for electric vehicles. So it's not the CS folks, it's the materials folks. Again, so we said, which was probably, I don't know, the right thing to do. We should have asked for money rather than saying, oh, we want to be able to publish the work. So we worked on that particular project in industrial design setting, where, first of all, to test materials, this is the problem we face. What is the next experiment we need to do? What are the next set of simulations we need to do? What materials we try? You prototype, but then you have to destroy, etc. So a lot of expenses, a lot of time, and so on. So the goal is to close the the loop quicker. And so, you have certain properties. Another problem is that you have very small amount of data. So we applied some of these techniques that we had developed, which resulted in certain prediction errors, which were much lower than what they had seen. It saved them huge amount of time and money in deciding what experiments to do next. Okay, so I'm going to sort of close this talk with the following chart, which essentially shows where does AI fit in and what are the challenges within the material space that as seen by us. And of course, this has been also written. So one is the forward modeling. Given a material, can you predict different properties, right? And within that, you have small data samples that you learn from, maybe experiments, others, and then big data samples, right? So what are the techniques that we have seen that they work in these scenarios? What is challenging is the inverse modeling problem, which is essentially given a property, how do I design a material, right? Which is, of course, a holy grail of material science. Within that, there are two problems. Big design data space, so it's like billions of combinations. So I gave you an example of this, where you do forward models, but your inference time is small enough that you can scan the entire space to figure out, get an answer. And of course, in other scenarios, it's you need to do something. You can't apply this big hammer type of, forward model and then apply it for inverse design, because the design space itself is huge. So what are the solutions? What are the approaches? We don't know the answer to that. Some of these things, like can you use generative model like GANs, and can you do sampling, certain type of active learning, etc., in order to address this. And of course, all this requires high performance AI, ML algorithms, as well as computing. So with that, I'm going to stop, and thank you for your time.
Thank you very much.